Hello and welcome to Chapter 2. On page 27, pay attention to this introduction of notation. R, we're going to use it for nominal interest rate per year, not really the one we want to use. We want to use the effective interest rate per year, which is I. So now we have a new variable called R, and that's typically the quoted interest rate. For example, when you go to the bank and you see these interest rates announced on posters saying, like, for example, 8% for a personal loan. That's the nominal interest rate per year, not the effective interest rate per year. Then R prime is the nominal interest rate per time unit. The R and R prime do not need to be the same. For example, if this is the nominal interest rate per year and the time unit is months, then R prime will be equal to R divided by 12. M is the number of time units per year, but also used as the time frequency for the cash flows. And J is the time frequency of interest compounding. So what we are getting at is that the frequency of the cash flows does not need to be the same as the frequency of interest compounding. And that's the whole premise behind Chapter 2. Then I is the interest rate we are looking for, is the effective interest rate per time unit, okay, per interest compounding unit usually, and is the actual interest rate that we're going to pay, not the one announced. So how can we infer from the nominal interest rate, the one quoted, how can we figure out the effective interest rate? To do so, we're going to deal with three cases. These three cases are enumerated on page 28 at the top. Case 1, when J is equal to M, meaning when the frequency of interest compounding, J, is equal to the frequency of the cash flows, M. Second case, when interest compounds more frequently than the cash flows are made. So for example, let's say we have daily compounding of interest and monthly cash flows. So here we're trying to assess which time unit is more frequent. We're not saying that days are greater than months. We are saying that days happen more frequently than months. And lastly, the third case is when the opposite relationship is true, when the frequency of interest compounding is smaller than the frequency of the cash flows, when interest compounding occurs less frequently than cash flows are made. The most common case is case 2. Now, let's take this example. Becky deposits $600 every month in a savings account that has a nominal interest rate of 24% per year. How much will she have at the end of 3 years if interest compounds monthly? So the first thing we do in these scenarios is to assess the relationship between the frequency of cash flows and the frequency of interest compounding. Let's start with the interest. So J, for interest compounding. J happens monthly. Interest compounds monthly. So J is in months. And the cash flows, Becky's deposits, happen also every month. So M is also monthly. So from here we conclude that J is equal to M, and therefore we're talking about a case 1 scenario. In a case 1 scenario, the effective interest rate is merely equal to the interest rate, the nominal interest rate per compounding period or per payment period, because they are the same. So the interest rate that we should use, the effective interest rate, it's equal to the quoted interest rate divided by how many cash flows are there within that time unit. So note that the interest rate is 24% per year. We're going to have 24% per year. And how many cash flows are going to be in a year? Well, it's monthly, so there's 12 cash flows per year. So the interest rate is 2% per month. There are 12 monthly payments, so the frequency of the cash flow is monthly. We're dividing year per month, so the ruling unit at the end, the result is the one in the denominator, so per month. It's 24% per year, which means 2 per month. Once we figure out the proper interest rate, then we use the formulas we already learned in chapter 1. Here we're talking about an annuity of $600, an annuity that happens every month. Recall that it's called annuity because it's a constant cash flow in regular time intervals. The intervals here are months. So even though it's called annuity, it doesn't need to be per year, per annum. It's per whatever time unit we are talking about. Here, as long as it's constant and happening in regular time intervals. So it fits both premises. It's constant, it's always $600, and happens every month. So we're talking about an annuity of $600 per month. And the question asks, how much will she have at the end of 3 years? Right? So it's the future value of this annuity at the end of 3 years. Now note, what's going to be the time unit for our timeline? They asked how much is going to be there at the end of 3 years. The same is to say, how much is going to be there at the end of 36 months, given that interest is compounding at 2% per month. So we need to envision everything in months. So the future value of an annuity formula that we know from chapter 1, and then plug the data. So we are looking for the future value, given that the annuity is $600, the interest rate is 2% per month. There's going to be 3 years, so 36 months, then minus 1 divided by 0.02. And therefore, Becky is going to have $31,196.62 in this account. So the point was figure out the proper interest rate to use and the time unit of reference. The question is stated in years, interest rate per year, how much is going to be there at the end of 3 years, but the cash flows happen monthly and the interest compounds monthly. So we need to envision everything in cash flows, compounding frequency. Now, what if interest compounds daily? So Becky is going to make $600 deposits every month for 3 years, but this time she's earning interest daily. So the frequency of compounding, which is days, is greater than the frequency of the cash flows. So we have J is in days this time, and the cash flows remain in months. So the frequency of J is greater than the frequency of the cash flows. So this is what we refer to as a case 2 scenario. The computations to find the effective interest rate are slightly more complicated because they involve 2 steps. Step 1. Find R prime, which is equal to the nominal per payment period, per cash flow period. So this is the computation we did before, 20% per year, and there's going to be 12 payments per year, or cash flows, right? 12 months. So we still have a nominal interest rate of 2% per month. Step 2. Use the formula shown in the textbook, which is the effective interest rate is going to be equal to 1 plus r prime that we just found divided by j, divided by how many times interest is going to be compounding within cash flows, in between cash flows. So 1 plus r prime divided by j to the power of j minus 1. Right? We're looking for the interest rate. So here we did 1 plus this ratio. Then we have to take the 1 out, so it put minus 1. So we get the interest rate that effectively is being earned in between the cash flows. So the computation will be 1 plus 0.02, again the interest rate's being written in decimal form, divided by, so this is 2% per month, and then you have to ask how many times is going to interest be compounding in between months. So if the interest compounds daily, in terms of accounting, there are 30 days per accounting month. So even if we're talking about February, we're going to count it as having 30 days. Even if we're talking about January, which has 31 days, we're going to use 30. So in accounting, there is 360 days in a year, 30 days per month. In reality, it's 365. But for accounting purposes, in finance, we're talking about 30 days per month. It's a simplification, a proxy. So we have 1 plus r prime divided by j to the power of j minus 1. This will give 0.0202. Always leave at least 4 decimal places, okay, in your computations. Don't leave just 2 decimal places. Leave minimum of 4, or keep it all when you are doing the computations in a laptop or in a calculator. Leave as many decimal places as you can, because the more decimal places you leave, the more accurate your answer is. If you're doing it by hand, like I'm doing it, then leave at least 4 decimal places. So you end up with 0.0202, which means 2.02% per month. So we still envision everything in the frequency of the cash flows, right? But given that the interest rate was compounding daily, we need to figure out, okay, so then what is the proper interest rate to use per month? It's not 2% per month, it's 2.02%, slightly higher because of the frequency of compounding being higher than before. Before we were just earning interest every month, now we are earning interest every day. And this is a very common scenario when, for example, you deal with your credit cards or any kind of financing. So we found out that the proper interest rate to use in our formulas, the I in our formulas, is 2.02% per month. So we're going to compute the future value of an annuity, just as before. 600, that was the annuity, 1 plus the interest rate, which now is 2.02%, therefore 0.0202, to the power of 36 months, because it's a 3-year long investment, minus 1 divided by the interest rate of 0.02. And this will allow Becky to have $31,316.91. So slightly more than before. If the interest was compounding monthly, she was having $31,196.62, and now she has 316. So about $120 more because the interest is compounding more rapidly, daily, instead of monthly. So she earns more interest. Now let's look at the scenario where the reverse relationship between interest compounding and cash flow frequency holds. So let's say that the cash flow now compounds quarterly. So again, we start by assessing the relationship between the frequency of compounding, which now is quarterly, every quarter, whereas the payments still being made monthly. So quarters, the frequency of compounding, happen less frequently than months, the frequency of the cash flows. So this is what we call a case 3. In the case 3, there is a twist. What we're going to do, since interest is only earned quarterly, and in between quarters whatever happens is not earning interest, because what matters to earn interest is how much is there at the beginning of every quarter. What you put in between quarters is just accruing to the next value for how much money is in the account the next quarter, but it's not earning any interest what is in between. So we're going to aggregate the cash flows at the quarterly level because they are not earning interest in between anyway. Let's visualize what I'm saying. The real timeline looks like this, right? Nothing in the first month, right? If nothing is stated that is beginning of the period cash flows, we assume that is end of the period cash flows. Every time we are asked to deal with beginning of the period cash flows, that will be stated explicitly in the question. If nothing is stated explicitly, then you assume end of the period cash flows. So there's nothing in the first month, and then Becky starts putting in $600 every month. Because this is a case 3, we need to envision everything in the frequency of compounding quarters. So a quarter of a year, which has 12 months, a quarter has 3 months, right? There's 4 quarters in a year with 3 months each. So a total of 12 months divided in 4 quarters. If you were talking about semesters or semi-annual payments, then that will be 2 payments per year. Semi-annual means half a year, 6 months, a semester. There's 2 semesters in the year, so semi-annual payments or semi-annual compounding would mean twice a year. Quarterly compounding means we're going to have 4 quarters in the year, and every quarter corresponds to a period of 3 months. So the first quarter is here, the second quarter is here, and so on, till we will have 12 quarters at the end of 3 years. Now, at the beginning of the quarter, there's nothing there. So this first quarter, Becky earns no interest at all, because the money that is going to earn interest is how much is there at the beginning of the quarter. When the first quarter ends, she has how much? She has $1,800 there. She has these 3 cash flows, right? She deposits $600 per month. So at the end of the first quarter, there's going to be $800. These $800 are going to earn now interest for this quarter. In the between quarters, the first and the second, she is continuing to deposit $600 every month. So at the end of the second quarter, there's going to be a new amount of cash flow deposited, aggregating to $800. So we can say that at the end of every quarter, there is an annuity of $1,800. So the question is, given this annuity of $1,800 per quarter and that interest compounds quarterly, how much money is she gonna have at the end of 12 quarters, at the end of 3 years? So what we have to do in case 3 scenarios is transform the timeline into the frequency of interest compounding by modifying the amount of the cash flows. And this modified cash flow is nothing more than the aggregation of the cash flows that are happening in between time unit of compounding. So what we have done was basically to turn J equal to M, being M prime here, just to remember that we modified the cash flows. We turn it from months into quarters. We know consequences because the interest compounding is only quarterly. So this money is not earning interest anyway. We can add them up. And once we did that, we basically set this relationship equal. The frequency of compounding is equal to this modified frequency of cash flows. So we are back into a case 1 scenario. We transform the case 3 scenario into a case 1 by aggregating the cash flows to the unit of interest compounding. As such, the effective interest rate then is merely equal to R prime again, where R prime this time is equal to R divided by M prime, the new frequency of cash flows. So let's solve this backwards. So I, it's equal to the 24 per year, 24% per year, divided by how many quarters there are in a year. So there are 4 quarters in a year. So this means that we're going to have 6% per quarter as the proper interest rate to use in our computations. The interest rate per quarter, per the modified time frequency of the cash flows. So again, once we get to this point that we know which interest rate to use, we go back to the future value of an annuity formula and solve as before, adapting the frequency of the cash flows, interest rate, and the N to the new frequency. So 1800 per quarter, therefore we need an interest rate per quarter. We found it to be 6% per quarter. The N is in quarters, 3 years as 12 quarters, then minus 1 divided by the interest rate per quarter. Note that every time you do these computations, everything has to be in the same time unit. Annuity per quarter, interest rate per quarter, N per quarter. If you mess one of these things, if you put cash flows in months but the interest rate in quarters and whatnot, then you get the wrong result. One way to do a self-robustness check is to verify if I'm using cash flows, interest rate, and the N all in the same time unit. So if Becky earns now interest quarterly, what do you think is going to be the amount of money that she gets? Greater or smaller than before? As you can probably guess, given that interest now accrues more slowly, just every quarter, then she's going to get less. Becky gets $30,365.89. So clearly the lowest figure from the 3 scenarios of interest compounding we saw. Why? Because interest is accruing slower. So in essence, this is chapter 2. Figuring out the proper interest rate to use in the formulas that we learned in chapter 1 by paying attention to what is the relationship between the frequency of cash flows and the frequency of interest compounding. The cases we were dealing in chapter 1 were all case 1 scenarios. You were always given a situation where the frequency of the cash flows was equal to the frequency of the compounding. From now on, you can be given scenarios where that relationship does not hold. The most common scenario is when the frequency of compounding is higher than the frequency of the cash flows, what we now call case 2 scenarios. This case 3 scenario that we just did here is the least frequent of them all. That's all for chapter 2. Please go over the textbook, because it's great in terms of solving the exercises step by step. They use plenty of exercises to illustrate these concepts. Here I try to do exercises other than the ones in the textbook. And you also have those practice exercises at the end of the textbook.